So we've covered flow control, which is about not overflowing the receiver. Error control is about if we lose data or we have errors in our data, how to fix that. So in real life, things are not perfect. When we send data, there may be errors in the link. So we need to be able to detect those errors and correct them if possible, fix them. We can think about when we're looking at data link control protocols, we're transmitting frames, a collection of bits. So in terms of errors, we can have lost frames. A source transmits a frame, and because of an error on the link, it doesn't get to the destination. So something's transmitted, it's not received at the destination, we'd say that frame is lost. That's an error. Another type of error is that we transmit a frame, the frame reaches the destination, but there are bits in that frame that are in error. That is, if the frame contains 100 bits, maybe some of those bits are wrong. That is, they are transmitted as bit 1, they are received as bit 0. We call that a damaged frame. A frame that's received, but it contains errors. In both cases, we need to deal with them. We need to be able to detect that there are errors and correct them. The common techniques that we have for error detection and error correction, we've already seen one of them, using parity check and CRC checks for error detection at the receiver, and using forward error correction where the source, instead of transmitting the original bits, transmitted a code word that represented those bits. And if the code word was structured in some way that the receiver could determine if there was an error, and in some cases also correct the error. That's one case of error detection and correction. Other approaches that are used include using positive acknowledgements. So you transmit a frame from source to destination. If the destination receives that frame and that frame has no errors, it sends back an acknowledgement saying, thank you, that frame that I received is correct. If the source doesn't receive a positive acknowledgement within some time, it may retransmit that frame. So that's the other error control mechanism. You transmit a frame, the destination is supposed to respond with a positive acknowledgement. You wait for some time for a positive acknowledgement until some time limit is reached, some timeout occurs, at which point you decide, okay, I haven't received the acknowledgement, something's gone wrong, I'll retransmit that frame. So this is the mechanism of retransmitting a frame after some timeout, because you assume that there was an error on the link. And we can also have a concept of negative acknowledgements. You transmit a frame, the receiver detects that there's a problem and responds with some acknowledgement saying there was a problem. Please retransmit. These three mechanisms of acknowledgements and retransmissions are referred to as automatic repeat request techniques, or ARQ techniques. And they are the main form of error control used in many data link control protocols. Three versions that we're going to go through, they are general versions and they're used by different specific protocols. So there's general concepts, stop and wait, ARQ, go back N, and selective reject. We'll see that they're closely related to the flow control protocols. Stop and wait ARQ is very similar to stop and wait flow control. Send a frame, wait for an ACK. But it implements these retransmission schemes. Go back N and selective reject are very similar to sliding window flow control. Send multiple frames, a window of frames, wait for an ACK. If there are errors, retransmit. So they're closely related to the protocols we've gone through. But they include error control. And in many cases, a real protocol like TCP, for example, which is used for not the data link layer, but for error control and flow control, uses these mechanisms. Uses both flow control and error control mechanisms. So let's go through those three cases, spending most time on stop and wait, ARQ, and then the last two. Based on stop and wait flow control, send a frame, wait for an ACK. Once we receive that ACK, we can transmit another frame. But now, when we send a frame, the source starts some timer because we expect to receive the ACK within some timeout period. So that's the new thing here. We start a timer and maintain a copy of that frame. So I transmit the first frame, now I start my timer, store a copy of that first frame in memory at the source, and if I receive an ACK, everything's okay and I can move on to the next frame. If I don't receive an ACK before my timer reaches some limit, we say some timeout occurs, then I'll retransmit. So if ACK received, everything's fine, stop the timer, move on to the next frame, which is the same. Transmit a frame, start a timer, wait for an ACK. But if our timer reaches some limit, then retransmit a copy of the frame that we just sent. So that's our error control mechanism. If we don't receive an ACK within time, send again. And the destination, when it receives a frame that has no errors, it will send an ACK. So receive a frame, if there are no errors, everything's okay, transmit a positive acknowledgement in reply. If it receives a damaged frame, that is, if the receiver receives a frame that has bit errors and it detects those errors, it discards that frame, ignores it. It doesn't respond, it treats it as if it never received that frame. So a damaged frame, a frame with errors, is ignored or discarded by the receiver. A lost frame is not received by the receiver, so therefore there'll be no ACK. We'll go through an example to illustrate these processes. We'll see also that we need sequence numbers in stop and wait ARQ. In stop and wait flow control, we had no concept of sequence numbers. We introduced sequence numbers for the sliding window mechanisms. But now, after we go through the examples, we'll see that it's important to have a 1-bit sequence number for stop and wait flow control. With 1 bit, we alternate between the values 0 and 1. Let's go through the examples before we see why that's the case. Just an example here where A has some data to send to B. It's using stop and wait flow control. The first data frame, we're giving a sequence number 0. We transmit that data. B receives it. B delivers the data to the destination, that is the application or the next higher layer at B, and responds with an acknowledgement. And remember, in all the protocols we're dealing with, the acknowledgement number indicates the next frame expected. If B just received data with sequence number 0, it sends back an ACK saying, I expect to receive data with sequence number 1. So we've seen that in all of our protocols so far. That's no different from what we've seen in stop and wait flow control. A, after finishing transmitting the data frame, started a timer. Although it's not shown in this diagram, it starts a timer waiting for an ACK, eventually receives the ACK before the timer reaches its limit, and when it receives the ACK, it's allowed to send the next piece of data. And we use the next sequence number. Sequence number 0 and then sequence number 1. Transmit the data. Data is received, processed, just illustrating that it takes some time to process the data. Delivered to the next higher layer, send an acknowledgement saying, thank you, the next sequence number for the data I expect is 0. Because we have a 1-bit sequence number, we just alternate 1, 0, 1, 0, 1, 0 all the way. And continue. This is the perfect case where there's no data lost or no damaged frames. So this is the same as what you've seen with stop and wait flow control. Nothing new there, except the sequence numbers are introduced. This is the one that we're interested in. So let's work through the board. On the board, what would happen if we lose data? Let's say we transmit a data frame, and as I used in the previous diagram, I'll just indicate the sequence number of that frame in brackets here. So data frame with sequence number 0 is transmitted, and just to indicate that that frame is lost, let's just draw it like this. That is, A transmits the frame, but there's an error on the link such that B does not receive that frame. Source A, after completing the transmission of the frame, expects that frame to propagate and eventually receive an ACK. It starts a timer at this point and waits for that timer, or waits for an ACK. If an ACK is not received within some fixed period of time or predefined period of time, then it will retransmit. So we need another parameter, which is, say, the timeout interval. Let's say it's here. When I say a timeout, I mean that the timer expires. So a parameter of the stop and wait protocol is the timeout period, or timeout interval. E.g., some period of time. That is, start the timer here. After 50 milliseconds, in an example, if I haven't received the ACK, then retransmit. The value of the timeout period should be defined for the protocol. So in our case, we transmitted the frame. The frame was lost. We don't know that. From source A's perspective, it doesn't know it's lost. It just transmits onto the link. It doesn't know what happens on the link because it's just sent a signal onto the link. It doesn't know what the device at the other end point of the link receives. B, of course, doesn't receive anything. They don't have a frame that they've received, therefore they're never going to send an acknowledgement back. So from A's perspective, we're waiting for the ACK, we're waiting, we've waited long enough. Our timer reaches the timeout period. At this point, we'll retransmit. Send the same frame again. That is, the contents of this frame and this frame are the same. And we have the same sequence number as well. And let's say everything works okay in this case. That is, the frame gets delivered to the other side. Destination B processes that and everything's okay. It's not a damaged frame. Responds with an ACK. Received data with sequence number 0. Responds with an ACK sequence number 1, or acknowledgement number 1. And that data was delivered. That is, the data was successfully processed at B and delivered to the higher layer. And respond with an ACK. Of course, after A transmitted or retransmitted this frame, it started the timer again. But it receives the ACK before the timeout period. So if the timeout period was down here, it receives the ACK beforehand. So once it receives the acknowledgement, it stops the timer and moves on to the next frame. So although running out of space, the next frame transmitted, if we have data, is data with sequence number 1, the next piece of data that we want to communicate. And we continue as normal in this case. So this is illustrating a retransmission when a timeout occurs, because we lost the frame. So the timeout period, how long we wait, is a parameter of the protocol. So if you implement your own protocol, you'd have to specify what is the timeout period, what is the exact value of that.
So we have to set appropriate amount that should be more than normal cycle.
Yes. What's a good value of the timeout period? So the timeout period, if we need to set a value, what value should it be? It should be large enough that gives B the opportunity to respond with an ACK. As we see here, the data was successfully delivered, the ACK came back, which took this amount of time. The timeout period should be larger than this amount of time. That is, it should give B an opportunity to respond. If it was less, if the timeout finished here, that means we propagate the data, transmit and propagate the ACK. Even if everything works fine, no data lost, if the timeout was here, we would time out and retransmit, which would be wasteful because there's no error. So the timeout period should be larger than the normal time it takes to get an ACK back, which is what? Propagation of the data, any processing of the data, transmission of the ACK and propagation of the ACK. In some cases it's easy to know what that will be. That is, if I use a protocol for a link, then I may predict what the propagation time is going to be. It's going to be no larger than so many milliseconds. If I know the maximum distance of a link, I can predict the propagation time. If I know the size of the ACK, I can predict the transmission time. If I can predict an upper limit maybe of the processing time, let's say the processing time will be never larger than so many microseconds, then we can predict a good value for timeout period. It should be slightly larger than this time. Propagation plus processing plus transmission of the ACK plus propagation. The problem in practice is on links where we cannot predict those values, or in links where those values change. Why would the propagation delay change? Maybe you're using a wireless link and you're moving. The distance changes. In some cases, the transmission speed may change. That is, we may be able to vary between data rates. So these values cannot always be accurately predicted. Choosing a good timeout value is not easy. But in general, it should be larger than the time it takes to receive the ACK in the normal case. It should not be too large, because if it's very large, if we lose data, we'll wait a long time before we retransmit. So that's the trade-off there. Large enough to give B a chance to respond, small enough such that if we lose data, we don't spend a lot of time waiting. What happens if we lost this data frame? What would happen? If the retransmission, there was an error on the link and we lost that, what would A do? Time out and send it again. And there was another error lost, another data lost. What would it do? How long will it send again? And send again? And how often? We have to have an upper limit on how often we send again. So another parameter we'd say is let's say the maximum number of retransmits. So if this frame was lost, we would time out, retransmit, and if it happened again and again, time out, retransmit. We'll only retransmit a maximum number of times. If we've retransmitted some maximum number of times, then we'll assume some errors occurred. And A, who received data from the application or the higher layer, if it tries to retransmit the maximum number of times and still doesn't receive an ACK, it will report an error to whoever delivered the data to it. In the similar style, when you try to connect to a website, and if your web browser cannot connect, eventually you get an error displayed on your web browser saying, I could not connect. That's the same concept here. Try multiple times. If we try the maximum number of times, then we cannot deliver the data. We've got an error. So these are two parameters need to be defined in any protocol, any stop and wait error control protocol.
If we more than maximum commit, we will hold the system.
So what we're trying to do is deliver one piece of data from A to B. If we reach the maximum number of retransmits, it's as if we say give up on that piece of data, maybe move on to the next piece of data. Tell the application that we had an error with that piece of data. You'll have to deal with it in your own way. That may create an error in the data transfer, but something else needs to deal with that. Stop and wait will not. Maybe the user will need to deal with that in that they will need to try and transfer the file again. Or another protocol will. So that's simple. If we lose data, time out, retransmit. What if we lose an ACK? Transmit some data. And just to make note, what the data is being transmitted is data that comes from the higher layer. That is, the network layer delivers data to be sent to B. We transmit that data in a frame. That is, we attach some header, put the data in a frame and send it. So to note, this frame contains data 1 from the higher layer. Transmit that. Everything's okay in the data frame transmission. Processed by B. B delivers the contents of this frame to the higher layer at B. So now data 1 is successful. The application has delivered the data to A, that is sent it in a frame, and we've transmitted an ACK in response. But we lose the ACK. B doesn't know that. What does A do? What's A going to do now? Same, which means wait for timeout, and retransmit. It started the timer. It's not going to receive the ACK, so sometime later it will time out and resend that data, which is a frame containing data 1. Don't confuse data with a lowercase with the uppercase here. This is a frame with a sequence number. The contents of that frame contains the first piece of data that came from the source. Maybe we have a second piece of data to send as well, and a third piece. This frame contains this data. So it's a retransmission. It arrives. What does B do? It needs to discard this data. B has already received the data in this frame. If we receive, so we've received the frame successfully. If we process that data, and if we did this, don't draw it, but if we did this, we'd have an error or a problem. If we delivered the same data to the higher layer at B twice, then B has received that data twice, which is not intended. It was sent just once, it should be received just once. Imagine the data, the message inside this frame is data 1 means increase Steve's pay by 10,000 baht. We send that, it's delivered to B and it's processed by the user at B and they increase my pay by 10,000 baht. Then, because the ACK is lost, the protocol retransmits, B receives that. If we deliver that data again, then we've increased my pay by another 10,000 baht. Good for me, but not the intended operation. So we should not process this data, we should discard the data in this frame. And the reason we know to discard it is because of the sequence number. And that's why we introduced the sequence numbers. This frame had sequence number 0. We acknowledge that from B's perspective. So we're now expecting sequence number 1. We receive frame with sequence number 0, discard that, throw it away. Delete the data, because it's got the same sequence number as what we just acknowledged. Discard the data and acknowledge. Saying we're expecting to receive sequence number 1. And if that acknowledgement is successful, then A has the data acknowledged and can move on. And move on to the next piece of data. So this is useful, well, this is where the sequence numbers become useful, because B, the destination, can distinguish between two frames and recognize this is the same as this frame because of the sequence numbers. If we didn't have sequence numbers, there would be no way for B to know, even though the data is the same, how does it know that maybe A wanted to increase Steve's salary by 10,000 baht 2 times? If we didn't have sequence numbers, if B received data, it would deliver to the higher layer. If it received the data again, it's got no way to know whether it's a retransmission or if it's original data, but just looks the same. So sequence numbers are used to distinguish between retransmission or retransmitted data. Second act lost, same thing, or similar to over here where we retransmit. Yeah, we'd retransmit. If the act was lost again, retransmit up to a maximum number of retransmits. If it's not lost, say this act is lost, that we retransmit and the act is received, same. The B would discard the first data and discard the next amount of data. It will stop discarding data when it receives data with the correct sequence number. It's already delivered data with sequence number 0 to the other side. The next piece of data is going to have sequence number 1. Everything with sequence number 0 is going to be discarded. And that's the basics of stop and wait. Any questions before we move on to the next approach? Guaranteed a quiz question about stop and wait.
What happens if the time is the timer is short, the timer is shorter than the act? Like the act come after the timer.
Then we'll retransmit. If the timeout, so in this case, if the timeout was here, we'll time out before we receive the act and retransmit, which would be a bad thing to do. Retransmissions we want to avoid because they are wasting, or they're not wasting, but in this case, to deliver this piece of data to B, we started here and effectively we finished here. we moved on to data 1 at this point. Because we have a timeout, that increases the time of not sending data, and a retransmission increases the total time to deliver that data. So we want a small timeout interval so that we don't wait as long here, but we want a large timeout interval so that we give B a chance to respond. That is, for the act to get back. Throughput you could calculate the same as in the flow control, in that, let's say, well, if we just look at this data frame, we can look at how much data was delivered in this amount of time. You can calculate this time, transmission, plus timeout, plus transmission, propagation, act, transmission, propagation. You can calculate that time. How much data delivered? 1 frame of data. This one was not delivered to B. Only 1 was delivered to B. So the total amount of data divided by the total time.
The total time also includes like if fail, it also includes the timeout?
Yes, we think of the total time to get that piece of data to B. If we start here, we finish here, including this timeout.
When we count for the first attempt of delta 0.
When we calculate throughput, in real life, in terms of throughput, we don't look at an individual packet. We're normally not concerned about how long it takes or the throughput of one packet. We look at the throughput of a link over a long period of time. Imagine we send many packets doing this. Imagine every packet had 1 retransmission. So this is just 1 packet. Imagine we had 1,000 packets and they all took the same amount of time, because we send 1, it'll be lost, we retransmit, and so on. Repeat this 1,000 times and look at the total amount of data received divided by the total time, and it's the same as, okay, look at this one. How much data received in this amount of time? 1 frame. This one's not received. This one is received. Only 1 piece of data is delivered to the destination B. How much time did it take from here to here? And that would give us our throughput. The data size divided by the total time. Again?
You use this for as a representative of other frame. We calculate only this 1 frame to be.
Yes. If throughput is really the rate at which we receive data. But if we look at what's the maximum possible throughput if this occurs, then it takes this time to deliver 1 frame, and to deliver the next frame would take the same amount of time and the same amount of time.
We calculate by the real data for 1 frame divided by the
total time for 1 frame.
And if the frame is not like this, we have to average it.
If, for example, there were 2 frames in this question, this one and then the second one, and the second one was successfully delivered, no retransmission, then again, although it's not the best representation of what happens in real life, again you would calculate the total amount of data received, 2 frames, divided by the total time it takes to do all that. So it would be the average of those 2 in that case. If you had 1,000 frames, the average of those 1,000. Yeah. Yep.
After we retransmit, do we acknowledge the act?
Do we acknowledge the ACK?
Yeah.
No, because that would go forever. At the end, if we receive an ACK, then that's it. If we receive the ACK, then and everything's okay, then that means that data, that piece of data has been acknowledged. Move on to the next piece of data. Does that address the question?
It's something like this. If the timeout is short.
Okay, I see. Yep, understand. If the timeout is short and we time out and then receive the ACK, if we time out at this point in time, because our timeout was too short, then we start transmitting the data. And then we receive the ACK, then we could accept that ACK, or we could ignore it and wait for the next acknowledgement. We should receive another acknowledgement. In any case, we're going to receive 2 acknowledgements in that case. It'll be similar to this case, except this acknowledgement comes. Imagine we timed out and this ACK was delayed and arrives here. We receive the ACK, but we've already sent the data again. We're going to receive an ACK. We need to wait for the ACK for this data frame. It's still stop and wait. We've transmitted a data frame. We cannot move on to the next one until we receive the ACK. If we receive the ACK here, if we receive it here, we would think that this ACK is an acknowledgement for this frame, and that will be okay. The next ACK would be discarded because I've sent data. I haven't received an ACK. I retransmit, and then I receive an ACK. If that ACK is the correct ACK number, and it is, then it acknowledges this. I would assume what's happened is I sent my data, something went wrong, no ACK received, I retransmitted, I receive the ACK. Everything's okay from A's perspective. It can now move on to the next one. If then it receives this second ACK, it's got the same ACK number. Discard it. In the same as here, if we receive data with the 2 same sequence numbers, we discard the second one and subsequent one. Yep.
You like immediately acknowledge that and send the next one.
Let's draw it. Time out, retransmit. This ACK for the first frame is delayed. Takes a long time to get back. ACK 1. Data 0. Time out. Retransmit. ACK 1 arrives. From A's perspective, everything's okay. The data has been acknowledged. That is, A knows that the data they sent has been received and processed by the destination B. Whether or not this is an acknowledgement of this frame or this frame, it doesn't matter. It's an acknowledgement of the data being received because it's the same data. In fact, now A can move on to the next data frame.
And immediately move on.
After the ACK is received, yep. If we now receive an ACK for this one, sometime later, discard that ACK because it's the same as the previous one. It should alternate in numbers. It should be 1, 0, 1, 0, the ACKs, if everything's okay. If it's a duplicate, discard it. Same here with the data. If it's duplicate data, data 0, discard the second one and the subsequent ones.
So if the act comes while we are retransmitting the data, so that when you receive an act, then after you retransmit that, you immediately transmit the next one.
It may depend upon the implementation there. If we receive the ACK here, I think an implementation could decide what to do. It could just choose to immediately send the next data here. Or it could make a decision and think that, okay, that's a delayed ACK, something's gone wrong. That would be implementation dependent there. It could immediately transmit the next data. Yeah. Of course, this all assumes that we've got a full duplex link. Yeah?
What is the act with the same sequence number but came from another data?
What if ACK? What if an ACK? I think the question: what is if we get a delayed ACK and it's the wrong? It's considered the correct sequence number. So what would happen if this one was, if this data frame, transmitted, ACT, now we have a problem with what's happening on our link. So I think the point is, what happens if we transmit this data frame, get an ACK 0, transmit the next data frame, and then magically this one arrives? It cannot. Or we assume that we have a link here. What's happened? Somehow this frame has been delayed and this one arrives before it. That's very unlikely on a link, and in most links impossible. That is, we transmit this one and then this one, but we receive this one and then this one. When we transmit frames in order, they'll arrive in order or not arrive at all. They will not overtake each other. That is, for that case to happen, one frame is transmitted and then the other, and somehow the second one overtakes and arrives first. On a link, how do those signals overtake each other? Unlikely. So the assumption is that in the link, no overtaking of frames is possible. If it was possible, and it is possible in a network, in a link it's not possible, but in a network it is possible when we look at TCP, then we need some other way to deal with that. So it is possible when we look at later protocols, but not at this stage. So in that case, that's why a single bit sequence number 0 and 1 is sufficient. Stop and wait ARQ is simple, same as stop and wait flow control, but inefficient in the same approach that we can only transmit one piece of data at a time, then we have to wait a long time before sending the next piece. Apply the concepts of sliding window, allow the source to send multiple frames of data at once, or one after the other, and then wait for an ACK. And that's what go back N and selective reject allow us to do. It's all right, 15 minutes. 15, 20 minutes, and then we can have our quiz. We're almost finished. So go back N and selective reject use the same concepts of sliding window. We're allowed to send a window size of frames before we have to wait for an ACK. If there's no error, it's the same as sliding window. If an error is detected by the destination, then it will reply with a negative acknowledgement. This is an acknowledgement saying there's been an error. Positive acknowledgement saying we've received your data okay. Negative acknowledgement or a reject message. You'll see in the diagram it uses the word reject, saying we've received some data but there's been an error. Do something about it. And this is a key difference between go back N and the next scheme. In go back N, once the destination detects an error, it will discard the frame that indicated an error or had an error, and all future frames that it receives up until that retransmitted frame is received. Remember, with sliding window, we can send multiple frames. Let's say a window size of frames. Therefore, we may receive, let's say, 5 frames, frame 1, 2, 3, 4, 5 at the receiver. If the receiver detects frame 3 is in error, then what the receiver will do will discard frame 3 and frame 4 and 5. It will discard everything following that error frame, the error frame and everything following it. And it will ask, or it will indicate to the source there's been an error with frame 3. And what the source will do is go back and retransmit those frames that have already been sent, 3, 4 and 5. Transmitter must go back and retransmit the frame that was in error plus all subsequent frames that it has already sent. And that's where go back N comes from. We have to go back and retransmit N frames. We'll see selective reject. We can go back and retransmit just one frame. That'll be different. We'll describe this in the example. All right, it's a bit harder to see, but we have multiple frames being transmitted by A, frame 0, 1, 2, 3, 4, 5. So we have a window size still, same with sliding window. We can send multiple frames. In this specific example, we're sending an ACK after every 2 frames are received. It doesn't have to be that. It could be an ACK after every 1 or after every 3 or after every time, but it would be defined what it is. In this example, after 2 frames. Everything's fine. Frame 0, frame 1, send an ACK, and we, in the diagram and in the textbook, it refers to as a receive ready. A positive ACK is saying, I've received frame 0 and 1, I'm ready to receive frame 2. So this is really acknowledging 2 frames received, 0 and 1. I receive frames 2 and 3, it'll receive an ACK or a receive ready saying, I'm ready to receive frame 4. So this is normal sliding window concepts, nothing new. A has transmitted 4 and 5 and also subsequent frames, 6. Frame 4 has an error and is lost in the link. So B has received 0, 1, 2, 3 and eventually receives frame 5. And that indicates an error. We should receive frames in order. Sequence numbers need to be in sequence. We've missed frame 4 from B's perspective. That indicates to B something's gone wrong. I will inform A something's gone wrong by sending a reject message or a negative ACK saying I'm expecting to receive frame 4. There's been an error. And B will discard frame 5, and if it receives subsequent frames which are not frame 4, it will discard them as well. So in this case, frame 5 is received, discard. Frame 6 is then received, throw that away. And coming back to A, after source A receives the reject message, it knows that there's been an error with frame 4, so it needs to retransmit frame 4 and all subsequent frames that were sent since 4. So A knows what it has sent. It has sent 0, 1, 2, 3, 4, 5, 6, and now receives the reject message indicating there's an error with 4, so it has to retransmit 4, 5 and 6. This is the go back and retransmit concept. Go back and retransmit n frames. 4, 5 and 6 are retransmitted, and B, once it starts receiving those frames, can now send a positive ACK or a receive ready. I'm now ready to receive frame 5. 5 and 6 arrive, I'm now ready to receive frame 7. So just stop here. That's the approach for go back N. If the destination detects an error because it receives either a damaged frame or it receives, as in this case, a frame out of order. We should receive the frames in order of sequence numbers. If we receive them out of order, 3 and then 5, indicates a problem with frame 4, reject, or a negative ACK message saying, please send frame 4 again. We transmit frame 4 and subsequent frames, 5 and 6, because 5 and 6 have already been transmitted since frame 4. And then eventually the ACKs will start coming back because these frame 5 and 6 are discarded, they're not saved in memory, and then we receive 4, 5 and 6. So we've in fact received 0, 1, 2, 3, 4, 5, 6, we've received in order, and we can continue. Then we proceed, and in this case it shows what happens if there's an error with an ACK. Here we acknowledge frame 6, saying I'm ready to receive frame 7, but the ACK is lost, or the receive ready is lost. So we have transmitted frames from A's perspective, we've transmitted frame 4, and we've received an acknowledgement saying B is ready to receive frame 5. In effect, frame 4 has been successful, and A knows that. Because if B is ready to receive frame 5, it must have meant that B has received frame 4. A has transmitted 5 and 6. It's waiting for an ACK for them. So, same with stop and wait. After transmitting a frame, start a timer. And wait for some period of time for receiving an acknowledgement for that frame. We haven't yet received an acknowledgement for frame 5 or 6. We've started a timer for frame 5. We reach some maximum period that we're willing to wait, a timeout period. Once that timeout period occurs, we haven't received an ACK for frame 5 within that period. Send a special message, which is an ACK request. Here it's designated a receive ready with a 1 bit in the header indicating this is a message requesting an ACK. So it's not containing data. The previous ACK received was this receive ready, acknowledging frame 4. We've sent frames 5, 6, 7, 0, but this ACK was lost, and that causes a timeout to occur for source A. So at that time it requests an ACK. Please send me an ACK, because probably a previous ACK has been lost. Sends this special ACK request message. If B receives that, it responds with an ACK saying, what's the next sequence number I expect to receive? B has received 4, 5, 6, 7, 0. The next one should be frame 1. Once A receives this ACK, or receive ready 1, it acknowledges all frames before 1, which is 0, 7, 6 and 5. So this is an ACK that in fact acknowledges 1, 2, 3, 4 frames. And then we can move on to the subsequent frames. So we have a special mechanism here. If we don't receive an ACK within the timeout period, ask for an ACK. Don't necessarily retransmit the data, send a special ACK request message. In the diagram it's indicated a receive ready with some bit equal to 1, the P bit. But in general, it's a request for an ACK. When we receive that ACK, we know which frames have been received. If this was receive ready 6, it acknowledges frame 5. If it was receive ready 0, it acknowledges frames 5, 6 and 7. It's receive ready 1, it acknowledges frames 5, 6, 7 and 0. And then we can move on to frame 1, 2 and keep going.
What if P bit equal to 1?
So in this specific example, a receive ready we think of as just an ACK message. And that contains a number of bits, the header essentially, and in this message, one of those bits, the P bit, is set to 1 to indicate this is a special acknowledgement message. It's an acknowledgement message which means request an ACK request message. So in the diagram it's called RR P bit equal to 1. The general concept is a request for an acknowledgement. Some special type of frame. So two new mechanisms here. If we receive frames out of order, tell the source with a reject or a negative ACK, and the source will go back and retransmit the frames since that error frame and the one sent after that. Go back and retransmit N frames. If we don't receive an ACK for a frame within some timeout period, request an ACK. And then B should send back another acknowledgement. And as with the sliding window mechanisms, acknowledgements can acknowledge multiple frames at once. This acknowledgement really acknowledges 4 frames at the same time. So they're the two mechanisms introduced with go back N. Yep. Missing this one. So think of after every frame we start a timer. Same with stop and wait. Start a timer, waiting for an ACK for that frame. Although it's not shown on all these frames, think in every frame we send, we start a timer waiting for an ACK for that frame. We've sent frame 4. We've received an ACK saying next frame expected is 5. So frame 4 has been ACKed. We've sent frame 5. We're waiting for an ACK. Waiting for an ACK. Look at A. It doesn't receive a receive ready or an ACK before the timeout occurs. Because this one was lost. The ACK was coming, but it was lost in this case. So it times out and does a special thing. It asks for an ACK. It requests an ACK. Request an ACK. Receive an ACK, which acknowledges everything before frame 1, which includes 5, 6, 7 and 0.
So in case that if like we send frame 5, 6, 7 and 0, what if 0 is in error and then within the timeout you send a request? Would you send like a reject?
If 0 was in error or was not received, this receive ready would be RR0. Because we've received 5, 6 and 7, we haven't received 0, we're ready to receive 0. And then maybe later we'll detect if we receive, let's say 0 was lost, frame 0 was lost. B has received 5, 6 and 7. It doesn't receive 0. It receives an ACK request. So it sends an ACK saying, I've received 5, 6 and 7. I expect RR0. And then if it receives frame 1, same as up here. We've received 5, 6 and 7. We didn't receive frame 0. We received frame 1. We'd need to send a reject message. That was the case if frame 0 was lost. This would be RR0, 1 would arrive, And from B's perspective, 5, 6, 7, no frame 0, 1, that's an error. We need to receive frames in order.
Then it will say like reject 0.
And reject, yeah. Reject here. Yeah.
For the, it is the right in the slide R1 is correct or wrong?
This is correct. That what I just spoke about was what if frame 0 did not arrive? What if frame 0 was lost as another case? But this is correct. The alternative approach is selective reject. Almost the same, and the ACK retransmission is the same. It's just that, so the same scenario, 4 was lost, 5 is received out of order. So we send a special message back to A, a selective reject message, saying frame 4 is in error. The difference now between selective reject and go back N is that in selective reject, B buffers or stores frames 5 and 6, stores them in memory. It tells A, go back and retransmit frame 4. A retransmits frame 4, it doesn't have to retransmit 5 and 6 because B stores them in memory. Retransmit frame 4, move on to frame 7. And now, because B buffered frames 5 and 6, it's received 0, 1, 2, 3. 5 and 6 are in memory, in a buffer. 4. And then it uses the 2 in the memory, 5 and 6. So it puts them back into order. And then it can move on to 7, 0, and so on. The rest is the same as go back N. In go back N, you don't buffer frames after the one has been detected in error. In selective reject, we do buffer those frames. And that means we don't have to retransmit all frames again, just the one frame, frame 4 is retransmitted. Frame 4, 5 and 6 were retransmitted with go back N because 5 and 6 were discarded. In selective reject, 5 and 6 are buffered, they're not discarded, only frame 4 is retransmitted. That's the difference there. Everything else is the same as go back N. And the trade-offs, only frames that are rejected or a timeout occurs are retransmitted. Subsequent frames are buffered. They are not discarded with selective reject. The trade-offs here, selective reject minimises retransmissions. That's a good thing compared to go back N. But the bad thing is that the destination must maintain some buffer, large enough to receive the window of frames. So extra memory is needed and extra complexity is needed. That is, it needs to put those frames back into order and keep track of the ordering. So there's the trade-off between go back N and selective reject. Selective reject is better, minimises retransmissions, but worse in terms of complexity and extra memory requirements. So if you want a very simple receiver, go back N is usually used. So in fact, go back N is more widely used than selective reject. Maybe in cases where retransmissions are very bad for performance, like satellite links, selective reject's used. That's, and here's a mistake, it should be 2 to the power of k minus 1. Remember we spoke about in the sliding window there's a maximum window size, and the same in selective reject. Yeah, so here's just a typo, 2 to the power of k minus 1. If no. Sliding window, I think if you go back, was 2 to the power of k minus 1. Selective reject. So here's a mistake in the slide. everything should move up in the brackets. We haven't discussed how that works or the significance of that at this stage. We may see it when we look at TCP. As with the stop and wait and sliding window flow control, with the ARQ mechanisms, you can do calculations of how long things take, throughput and efficiency. And that finishes this lecture, because last week we did cover how long a timeout, or actually we covered today how long a timeout interval should be. Not too long. How long should a timeout interval be? If it's too long, we waste time waiting for an act. If it's too short, we'll retransmit, not giving the source a destination chance to respond. We still have a few more minutes before your quiz. That's all right, you have plenty of time. Any questions? Tomorrow we have the next topic. The last slide is just listing some examples of real protocols. But we're going to spend a whole topic. We're going to spend a whole topic on local area networks, which use some of these protocols. But other protocols use the things that we've spoke about. And in fact, TCP, which we'll spend an entire topic on, also uses these concepts. So we'll see them in later topics.